everyone. Welcome to St. Louis County Library's virtual program, Science in St. Louis. This evening's presentation, sponsored by the Academy of Science St. Louis, is Building Safe and Sustainable Batteries with featured speaker Peng Bai, a PhD, Assistant Professor of Energy, Environmental, and Chemical Engineering, McKelvey School of Engineering, Washington University in St. Louis. I'm Sarah Jones, the Adult Programming Coordinator for St. Louis County Library. And before we get started, I wanted to bring to your attention a few helpful tips in case this is your first Zoom program. First of all, this is a webinar, which means you should be able to see and hear us, but we cannot see or hear you. We are recording this, so it will be available on our YouTube page within a few days, and we will be sending out I think you'll be made aware of that, but you can always check our YouTube page, and I'll have more information on that in a moment. At this time, I want to be sure you adjust the live transcripts. If that's something that you would like to use, you can adjust those settings under the live transcript button in the Zoom window, and you can hide or show the subtitles or make them larger or smaller in the subtitle settings if you like. We also have the chat box enabled. We will address questions at the end of the presentation this evening, but we don't want you to forget anything. So in the meantime, as questions occur to you, feel free to drop those in the chat. We do our best to answer as many questions as we can, but we usually get to them. All right, so the other thing is if for any reason you suddenly lose the picture, the video, or the audio drops out or something like that, we recommend that you do leave the webinar and try to get closer to your Wi-Fi router and then rejoin using the same link. And that generally helps because it's often a bandwidth issue, a connectivity issue when something like that changes. So those things should help. And again, we are recording, so you're not going to miss anything. You'll be able to pick up whatever you miss in the meantime when the video is posted. So you can check out a full list of St. Louis County Library's upcoming programs at slcl.org/events. In particular, I'd like to mention we're hosting a program about citizen science, community-based science next week with the Missouri Department of Conservation, and that will be on Monday, April 18th at 7 p.m., so right around our corner. And then, of course, the next Science in St. Louis presentation will be on May 12th. So you can sign up for any of St. Louis County Library's programs by going again to that link. And you may also want to take a look at St. Louis County Library's YouTube channel, where you may find some of the previous Science in St. Louis presentations, among many other recorded programs. But I would like to turn things over now to Rose Jansen, the Director of the Public Science Programs and Science Speakers with the Academy of Science St. Louis. And thank you so much for partnering with us for another great evening ahead of us. Over to you.
Okay, you're welcome. As Sarah said, my name is Rose Jansen. I'm with the Academy of Science St. Louis, and we're very pleased to be partnering with the St. Louis County Library to bring you tonight's Science in St. Louis seminar, Building Safe and Sustainable Batteries. For those of you who are not familiar with the Academy, I'd like to take just a moment to tell you a little bit about who we are. We're an independent science organization supported entirely through community contributions. At venues throughout the region, we connect science in the community through free and or very low-cost public talks, science seminars and workshops, and trips and tours that feature scientists and engineering professionals of both national and international renown. In addition to advancing the public understanding of science, it's our mission to inspire the next generation of scientists and science advocates, which we do by offering a full array of free and low-cost opportunities expressly for teens, such as our Teen Science Cafes, STEM Teens Youth Leadership Council, Junior Academy of Science, and the Regional Academy of Science St. Louis Science Fair and its Honors Division. This year, all virtual. We do have plans to transition some of our programming back to in-person in the near future. The Junior Academy is a pre-professional STEM membership organization for students from the full range of academic backgrounds in grades 6 through 12. It offers hands-on opportunities in science, engineering, and medicine. Teens can attend unique behind-the-scenes explorations of leading engineering, technology, and science labs of our region and participate in field opportunities and challenging and engaging science competitions. Now, all offered virtually online. and Junior Academy members make real-world connections, meeting top STEM professionals. You can find more information on the Junior Academy and all of our community-wide science events and programs by visiting our website at academyofscience.stl.org. You may also visit us on Facebook, Instagram, or Twitter. You may want to sign up to receive Academy e-news on our website, again, at academyofscience.stl.org, or jot your email address down in the online audience survey, which will pop up in the chat window a couple times this evening before you leave. I think that's everything I need to say. So with that, I'd like to introduce tonight's speaker, Dr. Peng Bai. Dr. Bai is an assistant professor of energy, environmental, and chemical engineering in the McKelvey School of Engineering at Washington University in St. Louis, where he also leads the Battery Analytical Investigation Group. He earned his undergraduate degree in automotive engineering and his PhD in mechanical engineering from Tsinghua University in Beijing, China, and completed his postdoc work in chemical engineering at MIT, where he became a senior postdoctoral associate and research scientist prior to joining Washington University in St. Louis in 2017. Dr. Bai's expertise is in inventing new analytical tools, both experimental and mathematical, to investigate the fundamental science in advanced electrochemical energy systems. With his expertise in physics-based mathematical modeling and analytical electrochemistry, his original research has been published in scientific journals, including Science, Nature Communications, Energy and Environmental Science, and Nano Letters. Research from the Bai Lab recently revealed the formula for building a perfectly stable sodium electrode, and his team has now discovered the formula for a perfectly stable and safe electrode. This past January, their National Science Foundation and Institute of Materials Science and 56 engineering supported research was published in the journal Advanced Energy Materials. He is the recipient of the 2014 Oronzio and Nicolo De Nora Foundation Young Author Prize from the International Society of Electrochemistry and the 2018 ISE Prize for Electrochemical Materials Science. And we are very pleased to have him here with us tonight for a look at building safe and sustainable batteries. So won't you please join me with a virtual round of applause in welcoming Dr. Peng Bai. Dr. Bai, we're going to turn it over to you.
Thank you, Rose. Thank you very much for the kind introduction. And thank you also for this opportunity to directly speak to our next generation scientists, engineers, and innovators. And today, I'm very happy to introduce to everyone about our recent research. And here is, let me share my screen and, okay. All right, so the topic today is to build safe and sustainable batteries. There are different possible routes to achieve this goal. And we are particularly interested in a system called anode-free sodium battery. And I will introduce why, and that would be the primary purpose of the primary goal for this talk. And first of all, I want to introduce that I have a group, research group, now have 7 students there, 7 PhD students, 1 master student, and our research is sponsored by National Science Foundation and INSIS, which is the institute at WashU, and IMSC, Institute of Material Science and Engineering, and the TSVC Giving Fund. And more information can be found on my website, and we're doing really fascinating things. And so today, I think I actually break my talk into several sections. The first part, we want to introduce some battery 101 information, basically to tell you why do we need batteries and why do we need better batteries. And that is really the motivation why we do the research. And then we ask ourselves, what are the key questions we need to focus on? So what are the scientific challenges? And this is basically try to shape or try to identify what is the objective we are going to achieve. And the third part is how do we understand and improve batteries? And this basically demonstrates what is the method we're actually using. And eventually, I think everything will converge to a single message that is the anode-free sodium battery, or its analog, like an anode-free lithium battery, anode-free potassium battery, anode-free whatever metal battery could be a very promising choice for energy storage. And it is promising because it could be safer, it will definitely be more sustainable, and it will be cheaper. And before you jump into the serious science, let's talk about some fun battery experiment you can do. This is really like a lemon squeezy experiment that you can use lemon or other grapefruit and some zinc plated nails or copper wires to create this fruit battery. And this battery, of course, you can use this battery to light up an LED bulb, but also if you engineer your system fairly well, you can charge your cell phone using this lemon. And believe it or not, you can also use this to start a campfire, okay? But there is also another very practical experiment you can try. So here is the video I'm going to show you that we will have multiple AA batteries dropping from a maybe 6-inch high to the tabletop. And so you will see that some batteries, after you touch the tabletop, it stays there. Some batteries bounced up, right? And the difference is that the full batteries, the state of charge is 100. The full batteries will stay there. The empty batteries will bounce up. So this is a very simple, very effective method to tell you which battery is full, which batteries are still new, can be used, and which battery you should feel free to discard. But anyway, this is something you can try. But whenever you want to do this or other battery experiment, ask an adult and to evaluate the risks. And battery is an energy-containing little device. It could be dangerous at some point. All right. So more seriously, batteries ubiquitous is everywhere in our daily life. For example, if you ever open some kind of cell phone, you can see that you have a quite large battery. And actually, 1/4 of the total weight of your cell phone comes from the battery. And for the electric car, for example, the Tesla Model S, it also have a battery, but it's a battery pack. It's huge. It's on the chassis. It's beneath the floor, the car floor. And again, the weight is about 1/4 of the total weight of this car. And even the cost is roughly 1/4 or even higher for the total cost of the car. And I also like, maybe as everyone here, I like robots. And for the advanced robot I show here, you can see that there is a gray backpack. And that gray backpack is actually a battery. Why do we want a battery? Well, robots need energy, right? It's hard to imagine that you have some robot carrying an internal combustion engine and moving around and serve you coffee, because it's like, putting a lawnmower on the back. So you can imagine how noisy that would be. So you need batteries that have high energy density and also is quiet. But unfortunately, our current technology, this is the state of the art already, that if the battery need to be charged for 3 hours for the robot to work for just 1 hour, right? So there are issues whether we can create better batteries that can store more energy in a small size, but also you can charge that fast enough, right? The other very important aspect that we need battery is about utilizing more renewable energies like the wind energy, solar energy. But we all know that the weather can change, right? There are clouds that blocking the sun and their wind can't stop. So you always have this kind of intermittent generation of electricity from the wind turbine or from the photovoltaic panels. So this is the point we need a battery. So firm up the energy. Then when we cannot generate any renewable energies, we can provide some green energy from this battery and firmed up energy for ongoing needs, right? So this is really just apparent I think nowadays many people that we really need next generation engineers, scientists, and innovators to work on the battery in the battery field. And here I want to demonstrate some types of batteries, typical batteries. So this one at this corner, this is you probably call it button battery or coin battery, and our lab can make this very easily. But there are also some other types of batteries. For example, a cylindrical battery, like our AA battery, and this kind of a prismatic or pouch battery, okay? And if you ever open up a battery for your power tools, and in this black case, you actually find that there are just many more cylindrical batteries. And a similar thing is true for the battery of electric cars. For example, this is the chassis for the Tesla Model S. And this is the battery under the car floor. And you probably heard that Panasonic is providing batteries for Tesla, but where are the batteries? Do you have this just a giant box of batteries? And you don't have to open it, and you actually can search online. And Tesla already made this model and disclosed the actual internal structure is that in this box, in this battery pack, there are more than 7,000 of cylindrical batteries being connected inside. And this is one type of a battery pack. And there are a lot of it, very dynamic innovations going on in Asian countries like China, Korea, and Japan. And one of the very famous new format is this so-called blade batteries, where you can see this. You have this very long battery that has a very high aspect ratio. That the length is about 3 feet. The height here is about half feet, and the thickness only less than 1 inch. Okay, so that's why it looks like a long blade, and it was determined to be the best format for to achieve a system level energy density while giving you very good driving range for the electric cars. But anyway, you are not supposed to open any batteries, including your AA battery, because again, it's an energy storage device, and sometimes it can become very dangerous. Even the liquid inside, is actually very corrosive. It can burn your skin. So be careful about when you handle your batteries. And today I want to show you schematically. So no matter what kind of a format, what kind of shape or size you see over there, and the internal structure of a battery are very similar. And if you open them, you will see this kind of a laminates or layer of sheets, okay? And here you can see that the gray part is the casing material, right? You need some packaging material. But the internal structure contains 3 different materials. The blue color indicate what we call cathode. Well, you don't have to worry about the name. Don't be intimidated by this name. It's just one electrode, okay? And you will need another electrode. And between these 2 electrodes, the other electrode is called anode. Between these 2 electrodes, you have this white sheet that is actually the separator. It's literally just a plastic film that has pores. And all this kind of laminated sheets are soaked in liquid electrolyte, okay? So that's pretty simple. But today I want to show you some kind of scientific stuff. That is the image observed by, characterized by the scanning electron microscopy. So here, if we look at the cross-section of this blue sheet, that is the cathode, and you will see that it is actually, there are actually 3 layers. In the middle is the aluminum foil. It's like the aluminum foil we use in our household. But this aluminum foil is coated, double coated, top side, bottom side, coated with these particles. And the particles are basically glued onto the aluminum foil. And this entire thing is called cathode, okay? 1 electrode. And then you will have this plastic film that has this, you can see the black dots there, these are the pores so that the liquid can go through, and the lithium ions can go through that. Then you will have the yellow part, which similar to the cathode. This anode is also contains 3 layers. The middle is the copper foil instead, And on either side, you will have this glued particles. And for almost all lithium-ion batteries, the cathode material could be different, but the anode are usually just the graphite particles that it has been proven to be the best material. Of course, you can, as demonstrated by this internal structure, have many layers of this. The reason of this double coating is that you can repeat this structure, adding another layer of separator, adding another layer of cathode, right, up and down. So you have this kind of a series alternating patterns there. And the battery, this word, means a collection of things, very well organized collection of things. So you have this kind of a repeating pattern over here. And to understand the science, we don't have to worry about so many layers. We can just focus on the minimum functioning unit. Okay, so that is what I show here. And you can see that we have the cathode, we have the anode, and we have a copper foil, and we have the aluminum foil. But we don't have to worry about the double coating. And we can really just focus in on the middle part. We start from the copper foil and going down to have the graphite particle, which is the anode, just one electrode storing lithium ions. And we have the separator, we have the active material for the cathode. Again, another electrode that can store lithium ions. And then finished by this aluminum foil. So starting from copper foil and add aluminum foil is an electrochemical cell, okay? So when you have this multiple cells within this single cylindrical case or this kind of prismatic pouch, and that is called a battery. Sometimes you would hear people talking about a cylindrical cell or prismatic cell. That's also valid. It's acceptable because in that scenario, they're referring to a battery pack that contains thousands of these individual batteries. That's why they consider each one is a cell, okay? But anyway, these terms sometimes are interchangeable. So you just remember that the very basic functioning unit in any battery is this kind of a 5-layer structure: copper foil, graphite particles, separator, another type of particles, and aluminum foil. And everything is soaked in liquid electrolyte. So you can have the lithium ions to swim around to find the sweet spot to either go inside the particle or come out of the particle. So now we have this kind of a minimum, the basic functioning unit. I want to talk about the mechanism a little bit. So here I have this sketch, and to compare with this actual photo, this is a electronic microscopy photo. But here we are zooming to a tiny part of the single particle, which reflect the crystal structure. The gray spheres are the carbon atoms that forming this crystal layers, where this purple sphere represent lithium ions. So lithium ions can go inside graphite, the layered structure, and stay there. That's why graphite is an ion insertion material for the anode, okay? And we will have the separator, and the separator will have the electrolyte, and so lithium ions can go out and get salvated and swim toward the other electrode. The other electrode will be another crystal, okay? And that crystal also have space where lithium ions can go inside and move around. And that is another ion insertion, but on the cathode side. So ion insertion electrode. 2 ion insertion electrode is like 2 bookshelves, okay? You have a bookshelf at home, that's the cathode. You also have a bookshelf at your school, right? So you can borrow a book from your school and bring that back to your home, and you will eventually return that book back to your school, right? So lithium-ion battery is like this. You have 2 sets of bookshelf, and you are moving books back and forth. And during discharging, so lithium ions will swim out of, actually migrate out of this crystal structure of the graphite into the electrolyte and go into the cathode. books come out of your school, go to your home. And at the same time that you will have the electrons going through the external circuit to light up a bulb, to drive a fan, to drive a toy car, like that. And when you charge the battery, the directions got reversed. All right. So this is a very basic mechanism of lithium-ion batteries. And the reason we call it lithium-ion batteries is that we are using always the lithium ions in this battery. In the graphite anode, it is lithium ion. In the cathode crystal, it is lithium ion. In the electrolyte, it is lithium ion. It is lithium ions everywhere. And it is lithium ions shuttling back and forth that enabling the charge discharge of the battery. And next, with now a relatively clear understanding of the mechanism, let's talk about, is there a way to improve the battery? And I think the most important goal for creating better battery is first to increase the energy density, meaning that for the same size of battery, can we store more energy that can last longer so that we don't have to recharge our cell phone every day? So in another word, with our current level of energy storage, can we shrink the size of your battery, right? So you can fit in another battery within your cell phone, right? So that's equivalent. So that boils down to the term energy density. Can we increase the energy density of the battery? And you already understand that the easiest way is to shrink the size. Can we do that? Is there an easy way to do that? It's like you have two, think about it, you have two bookshelves, right? And you want to reduce the size of this kind of a system, right? Combination of two bookshelves. The one way of doing this is to remove one bookshelf, just lay down your books, right? And here, we want to remove the graphite. The reason is that the graphite is really just the hosting material for the lithium ions. If you remove the graphite, you reduce the volume nearly by 1/2, right? Without sacrificing any energy, because you are using the same set of lithium ions, and lithium ions now will be plated onto the current collector, which is the copper foil. You remove the particle, but you still have the copper foil, as I illustrated on the left-hand side. Okay, but this is a very straightforward idea, but why didn't anybody actually achieve that? There's a catch, because it's not like laying your book very nicely, very, organized manner. Layering this lithium ions on top of a copper foil is very challenging because it grows this kind of tree-like structures. And that tree-like structures can develop very fine branches that can go through the separator and short-circuit your battery. And you don't want to short-circuit battery even from external circuit, right? Because that will generate a lot of heat. And this heat can eventually lead to fire and even explosion. Okay, so this is the actual thing thought as the root cause of many battery accidents, including the battery for laptop, for cell phones, and for even for electric cars, and even for the 787, the Boeing 787, the Dreamliner airplane. So that is what that identifies one of our research focus is for this kind of anode-free system. You remove the active particles that's storing the lithium ions. When you start plating lithium ions onto the copper foil, generating this metal structure, that raises the question of a safety issue, raises the question of efficiency. And on the other side, we have this cathode material. This is just another electrode, and you still have the particles. And imagine that the crystal structure is just a tiny part of your nanoparticle. And the particles what we're seeing on the left is equivalent to what I'm showing here. It is about a 10 micron in diameter. And how large is 10 micron? So think about our hair. The diameter of our hair is about 50 micron. Okay, so it's a very tiny particle. And in the battery electrode, you can see that it's not hard to imagine that for this very large handheld battery, there are billions of particles in there, right? And I would ask a question: when you turn on your battery, when you charge your battery or discharge your battery, which particles are working, right? Will all these billions of particles work at the same time? That's not a guarantee, right? So in our scientific terms, that on the cathode side, what is the modest scale performance, right? Which particle or which part of particle is working at a given time? And that is the other scientific question that we are focusing on, okay? So a quick summary of what I described is that for our anode-free system, as I and this photo picture showing over here, on anode side, we have to worry about the metal plating process. We remove the ion insertion particles. That's great because that saves the volume, but you'll still need the copper foil where you need to do the metal plating. And when you do the metal plating, how do you handle the non-uniform, very rough metal plating on copper foil? That's the key question. On the cathode side, as I said, that there are so many particles. Which particles are working, right? What type of particles are the most diligent ones, right? And how do we avoid these hotspots around these overworked particles, right? How can we create this kind of a very healthy culture in that battery that all particles can contribute, that we have this very healthy teamwork? And let's talk about the first part. And we said that the deposition, I just said that, right? I just said that the deposition or metal plating is not uniform. It's very rough. How rough will that be? And here I want to introduce one of our work using the transmission electron microscopy. And so here is the photo of that equipment. And you have this very tall column, and you have this kind of a window, you have this kind of binocular over here, binoculars over here, looking at some kind of image there, right? So the top is actual electron gun. You're shooting electron beams and to some samples. Where's the sample? The sample is actually inserted from this kind of a knob. And there is actually the holder going through that hole. And this holder, this is the actual photo of that holder tip. And you can see here, there is kind of a vacant space and where you can anchor a cell or load your sample there. And we have this kind of a liquid cell that can really just construct a battery environment and still allow electrons to go through to give us some imaging. And the size of this liquid cell is about 5 millimeter by 4 millimeter by 4 millimeter. It's very small. And this little window, here is a big picture, but the little window is just 1 micron by 1 micron. It's very, very tiny. And it's actually converging into 1 micron by 1 micron window. And so here, what I want to show you is a video. It's a sequence of images we took by using the TEM, the transmission electron microscope. And let's see what we will observe. And this kind of this dark gray stripe is actually patterned gold electrode. And this gold electrode is soaked in electrolyte. And when we close the electric circuit, we will have the metal plating on the surface of this gold electrode. And let's see what we will see. So I hope you can see this, that I can replay this. There is a tiny structure emerge out of the surface, right? It's like a whisker. It's like a hair growing from the root, right? That's why I mentioned in the title that we discovered a lithium metal whisker protruding or growing out of this gold electrode, okay? When we say it is rough, it is non-uniform, the growth is really just localized and it grows like a hair, like some biological systems, right? That's quite a huge surprising discovery. But remember that this process, if I can replay it, this is the actual timestamp. It lasts about 2 minutes, okay? But the batteries, we use battery for days, for a longer time scale. And the battery is much, much larger than the structure, the features we see over here. So we invented another testing platform. And so here, what I did is that I used some very small glass capillary, and I heated the middle part and pull it. And you can see that then I achieve a thinner part. It is thin enough that under the microscope, everything will be very, very nicely arranged in a single field of view, or in the viewing window, okay? And so then this is what we see. You can see that we do the observation whether while we are still applying the current to the system. So we are applying a constant current to this little capillary cell, and we monitor the voltage, we represented by this green curve. And at the same time, we check the morphology changes. So you can see here, after about 36 minutes, we already grew some very, very rough structure. It is actually a collection of the whiskers we just saw. But because we know a little bit more about the science, and we want to wait, okay? And there's something surprising will occur. And let me play the video. So I hope you guys can see the video that as the growth keep going on, that there is something different shoots out. Pay attention to the details. Pay attention to the details that initially, if you focus on the tips are being pushed from behind. It is rotating, it is translating, but at this special time, a different structure shoots out. And the growing process changes to something like adding up at the tip, right? It's not being pushed from behind. It is a fast advancing fractal structure shooting out from the collection of the whiskers, okay? And this is actually, this kind of a transition point is also reviewed by this sudden change of the voltage indicated by the green spike over here. And this is where we have the fundamental science coming, that you need to consider what is going on in the system, right? We can see the morphological change, but what we can't see by naked eye is that there is a concentration change in the liquid phase, in the electrolyte, okay? And then you have to solve the diffusion equation to get a characteristic time that is called science time. It's not because the sun we are playing around, it's because a pioneer called Henry Sand, he derived this equation more than 120 years ago. And that theory was applied to our battery research nowadays. And so I showed you that for lithium growth, you will have this transition from a very mossy, very ugly collection of whiskers, then transit to this dendrites and fractal structure, fast advancing fractal structures. And this is true for all types of lithium ion battery electrolytes. This means different salt, different solvent. It's like salt is like sodium chloride is the table salt, right? Solvent, water could be one solvent, but it cannot be used for lithium metal because that will be strong reactions. The liquid here we use are non-aqueous electrolyte that is compatible with the metals. But surprisingly, you know what? When we change the sodium, we discover something different. So let's check the growth of sodium metal in our capillary cell. So you can see that it grows like a big chunk, right? It grows like a rod. It's 100% solid. You don't see any pores. You only see this shiny facet, right? Extending into the electrolyte. And this structure has a scientific term that is ingot, but it really just means totally different from the whiskers, from the dendrites we see in the lithium system, okay? And this shiny flat facet indicate that we have ideally stable, ideally reversible process here. And this is exactly what we are looking for metal plating. And if this is the case, why don't we try that in a real battery? So we created that. But before we jump into the actual battery performance, I want to give you a comparison to see why this kind of a new discovery is important. Because here are two videos I want to demonstrate. The top one showed you a not so good electrode. It is still compatible with the metal electrodes. And this is the good electrolyte we prepared. And we are doing the cycling, charging, discharging, deposition, dissolution, plating, or stripping. But you can see that you will have, for the good electrolyte, always have this kind of shiny crystal-like structure, right? But for the not so good electrolyte, you quickly generate this kind of residual structures, like a whiskers we demonstrated in this lithium system, right? And that is apparently not so good. And if you put this into a real battery and do the test, eventually we'll see that for this kind of a structure within the actual battery, you will see so many voids that you want to have, because that's the sign of the compromise, the performance, the deteriorated performance. But for the good electrolyte, you always have the very smooth, almost a defect-free deposition surface or plating surface. So this is not so good, but we have a very nice choice, right? So now it's time, it's really the time, that because we show the ideal deposition and we show the ideal reversibility, right? So we put that into a real anode-free battery. And remember that, as I said, you can remove the particle for the anode, right? But you still need to have the copper foil to have the metal plating. You will still have the separator. You will still need the particles for the cathode. But still, you save almost nearly 1/2 of the volume of the original volume, right? And by doing this, we actually demonstrate the cycling performance of this anode-free battery. And for these two charts, it is the cycling performance. The horizontal axis is the cycle number. The vertical axis is the discharge capacity. So every time, how much capacity, how many charges can you deliver, right? How much energy can you deliver? You can see that the energy you can deliver stays relatively constant, okay? So this is actually, if you check the numbers, that we actually achieve a record high performance for compared with similar systems. And so by looking at this result, I want to stress that the necessity and the significance of this anode-free sodium metal battery, because it is more sustainable in the sense that you don't need extra anode material. You see, you remove all the particles, right, on the anode side. Basically, you remove one electrode, one of the two electrodes in the battery. And if you don't have the material, of course, you save a lot of money, right? Of course, you will save all the associated costs by mining the material, refining the material, and fabricating the laminates, right? That's why it's more sustainable. And also, you increase the performance. As I said, that the very important metric for battery is the energy density, right? So this chart demonstrates that different batteries actually have different energy density, either scaled to their mass, well, energy per kilogram, or scaled to their volume, the energy per liter. And you can see here, lithium-ion batteries are currently the dominant product in the energy storage field, and it can be used for planes and drones and power tools, devices, electric cars. There are other lead-acid battery. That's the battery in our regular internal combustion engine cars, and for grid level storage, you have some other options, sodium-ion batteries. But if you can remove the anode for the sodium-ion battery, that is the hard carbon, you will increase the energy density, both the volumetric energy density and the gravimetric energy density to somewhere here, because it's nearly doubled, as you visually just see by analyzing the area, by analyzing the volume. So that's why now the anode-free sodium battery, not only it is more sustainable, it is something can compete with lithium-ion battery. It provides a more sustainable alternative for lithium-ion batteries, providing the same performance, but with less cost, with a lower price, right? With a smaller footprint, energy footprint during their entire production process. And of course, I hope you would agree that by seeing this kind of ideal metal plating and their cycling, you understand that it is ideally stable, it's ideally highly reversible, so that you don't have to worry about this kind of a tiny structure going through a battery to create this internal short circuiting. So the remaining challenge then would be, what is the best cathode material, the upper electrode, right? We're talking about anode side for a long time, but what is the problem with the cathode side? Again, the key issue is that, do we have a healthy team working environment there? That is our next focus. But even that, even the challenge is still there. We have some good news. It's because the raw material to prepare the cathode for sodium battery is much, much cheaper. So this chart compares the price for the raw materials for lithium batteries, lithium-ion batteries, or sodium-ion batteries. Okay, lithium system, sodium system, these are the raw materials to prepare the cathode for lithium-ion battery or sodium battery. And you can see that you barely can see any blue features, right? Because the bar is so short. It's nearly just 1% of the price for lithium carbonate. So the price of a sodium carbonate is so low. And when you have this kind of a very, very low price for the raw material, you know that it will be much more sustainable, right? Even on the cathode side, we have been talking about the sustainability due to removing the anode, but for the cathode side, it's also very, very promising, okay? All right, so I think we still have some time, so let's keep going on the cathode part. As I said that I have been talking about overworked particles. What do you mean by overworked particles, right? And we will demonstrate that. Without diving into the mathematical analysis, we will just show you some videos. And the idea is that if you have the overworked particles, they become exhausted, they become so tired, and eventually they would not be able to continue working. Then physically there will be some very bad things happen, and you will have this kind of a hot spot in your battery. And the hot spot could be the origin of risks, okay? And all right, so let's start from this part. And as I said, that for our anode-free system, you remove the particles on the anode side, but you still have the particles on the cathode side, so the other electrode. Our idea is that, can we prove, or can I prove to you that there exist overworked particles? Showing by this schematic is that in the electrode, we have this so many particles. Do we have this kind of a full particles indicated by the gold color, 100% state of charge? So it's full, it's already reacted, it's fully reacted. But we also have some reacting particles where it is half full, 50% state of charge. And we have some sleeping particles. They're not even participating in any reaction just yet, right? They're probably lazy particles, right? We want to get rid of the electrode. So the idea is to identify which particles are more active, right? And for this purpose, we actually made this coin battery or coin cell, or button cell, or button battery that we use in our remote controller or car keys. But in this case, stainless steel case, we have this little hole, and we have this window to observe the changes of the particle. And here we use graphite as a model system for all ion insertion materials. And you can see here, this is again a video. And the graphite is exactly the material we are using in our pencil. And we all know it is black, right? This figure also shows that this graphite electrode is black. But graphite is the host material for lithium ions. Lithium ions can go into the graphite. So when the reaction goes on, and let's see what this video will tell us. You can see that this black color start to change. You can see some kind of a blue color showing up. And all of a sudden you will see this kind of orange or orangish red color showing up, right? So that means reaction with lithium ions, accommodating more lithium ions lead to a color change. And that's not the end. You yet again see another color, that is the gold color, because of more lithium ions coming into the graphite particle. So the gold means this particle is fully filled with lithium ions, okay? And the red part means that it is still half full, still more lithium ions can come into the particle. So you can see that maybe it's not so obvious, but definitely you can see that this happens sequentially and happen randomly, locally. It's not like uniformly going on everywhere. And to quantify this discovery, my student used this software, open source software called ImageJ that used in many biological analysis. And you can see that this is the graphite electrode that we take the picture using a regular visible light microscope. And you can see that the blue color, red color, eventually the gold color. And he zoomed in to take a part of this, just randomly choosing this local region and convert this color by using this ImageJ software, convert this color to some standard color, RGB color for later analysis. And he identified that, okay, shown on this diagram, initially, the area fraction is 1, but fully in the color of blue. The blue color will go down because the red color comes up. And then when you reach the maximum areal fraction of the red color, the blue color reach a minimum, meaning that almost all particles, all blue particles has been transformed into the red particle because more lithium ions have been accommodated into that particle. And after that, you start to see the emergence of the gold color coming up, and that the red color will now goes down. So this kind of an aerial evolution curve shows that there is indeed a sequential reaction process, right? It's not like everywhere, progressing at the same time, and all of a sudden it goes to full. And more importantly, we were able to demonstrate. Excuse me, I think my computer froze. All right. So here, what I want to show you is that on the left-hand side, this region, you can see this single particle. So this is we stitched the images of a single particle, but image of the single particle from different time steps, okay? So you can see that the particle is just about 5 micron in its width. And micron is micrometer, is like if you know 1 millimeter, that is 1/1000th of a 1 millimeter, okay, 1 micron. So it's a very, very small. In other words, as I said, that the thickness of the diameter of our hair is about 50 micron. So it's 1/10th of our hair diameter. So it's a very small particle. And surprisingly, using visible light optical microscope, you can identify the different domains of different colors. And you can even clearly see these color boundaries. Actually, we call it using scientific, that's a phase boundaries. And the phase boundaries are moving, are evolving, right? And this is the time, more fundamental science coming in, that when you see this phenomenon, can you translate this into a different language? The language of mathematics. And the language of mathematics is just equations. So we were able to model the system by using this equation, okay? And that equation can very accurately fit the curve. So the blue one is actually experimentally determined phase boundary or color boundary length. The total length is evolving, as you can see here. Initially, we don't have phase boundary, we don't have color boundary, and we have a length over here, and the length changes, and the length vanishes, and eventually, well, again, when another color comes up, it shows up again, and it eventually vanishes again. So we were able to, using this simple, well, probably not so simple equation, because we have the exponential term over here, to fit the experimental discovery very, very well. And that tells us what is the true physics during this process. And this example, an example of the transition of lithium whisker to dendrite, are very good examples showing you, if you know the basic science, you would have the patience to wait for some phenomena to come up, and then you would be able to use fundamental science to explain that very accurately. And when you have this accurate understanding, you would be able to create better systems. And the better system we identified through this research is the anode-free sodium metal battery, or its analog, anode-free other metal batteries. All right, so again, as I said, that we use graphite. You probably, the graphite is fantastic, it changes color, but not all battery parts can change color that you can visually see. But what I can share with you today is that, without the details, that if you look at images from different battery cathode materials, and you can see this kind of a contrast between green and the red, or even yellow and blue, that means the reaction in the electrode is not uniform. Okay, it's not uniform. There exists the overworked particles everywhere in all batteries, and we have to help them by designing new materials, by modifying the particles, or by designing a more friendly or more efficient charging or discharging protocol, so that more particles can participate the reaction and share the burden, and to create this very, very healthy teamwork culture in our battery. All right, as a summary, I hope I was successful in introducing some of the battery 101 knowledge, that at least I hope you can remember that the functioning unit, the basic unit in any lithium-ion batteries, contains a copper foil where you have graphite particles pasted glued on it. And then you have a plastic separator, and the separator separated another type of particles that is glued onto the aluminum foil, and everything is soaked in liquid electrolyte. So this is the fundamental unit. This is where the science is analyzed, discovered, analyzed, and improved. And next, I hope you understand that the anode-free sodium batteries is really a very good example to show you that without using the sodium insertion anode, the particles, without the particles, you save the material, you save the cost, right? But you have to handle the non-uniform metal plating. But we were fortunate to discover this chemistry and demonstrate the ideally stable, ideally reversible metal plating process, and to create this anode-free sodium metal battery. And on the cathode side, we have many cheaper, much cheaper choices. And And eventually, as I just stressed that and this is for the overworked particle, is not just a problem for the sodium, anode-free sodium battery, it's for all batteries. And because batteries use the electrode, and electrode contains billions of particles, there are overworked particles. We should pay attention to them. All right, with that, I thank you for your attention. I'm open to any questions. Thank you.
Thank you so much. So fascinating. And we have plenty of questions to get us started. The first, I think, someone asked, why do the whiskers grow in the first place? What causes those whiskers to develop?
Wow, that's a very good question. You know, that's a question every scientist in this field are asking. The reason, let me pull up this video. So the reason is that, so in general, whisker growth is a very fascinating problem. So you don't have to just think about the lithium whisker growth. There are tin metal growths in our electric circuit board. So sometimes you probably, I don't know whether you experienced that some devices, all of a sudden it doesn't work. But if you smack it somewhere, it starts to come back to work. It is because that there are tin whiskers growing in your electric circuit. And then when you smack it, that whisker got to break off and the device start to function back again. And here, the whisker growth is still a mystery. And we only have speculations, okay? The reason is that the electrolyte, the solvent we are using, is not ideally stable against the electrode. So it will have a reaction before the lithium plating. You will have a reaction between for example, the copper foil with your electrolyte. And the reaction product will create this kind of you can call it a passivation layer, but this passivation layer is not uniform. It's kind of having this pattern structure, and somewhere has easier access to lithium ions, somewhere is completely shut off. So that when you have this non-uniform or highly localized access of lithium ions, of course, the growth will preferentially focus to that sweet spot. And so this is really what people have been trying to verify experimentally. But this is still, I think I would say, still either we still don't have a conclusive idea on why it is grow. We know why it is grow there, but we not uniformly, but we don't know why it grow from the root. We don't know the specific reason. So if you're interested, read on, check some paper. There are very fascinating experimental techniques and analysis there, and in articles, scholarly articles, or scientific papers.
Thank you. That is so fascinating. And so we have a few more questions kind of related to whiskers. Someone asked if the whiskers will grow out of aluminum if the lithium ions are removed. And when you mentioned that the electrolytes are really seem to be the issue, but so maybe I'm not understanding the question perfectly, but that was something that someone had asked about the aluminum. Would it still happen with other metals?
Yeah, that's a very good question. So here, I think it could be challenging for some other audience. We have to come back to the names of the electrode, right? We have the anode, we have the cathode. Let me use the other demonstration. So this is an anode-free system. And we said that you will have whisker grow on the anode side. It is because you're plating metal on a copper foil. When you charge the battery, ions, you are right, for whoever asked the question, ions will move toward the cathode and toward the aluminum foil. But the problem is that you are not at the right potential to do this. So the condition does not allow metal plating. Okay, metal plating only happens when you have a lower potential, that where you can receive the electrons. And for the aluminum foil, on the cathode side, you don't have to worry about the lithium metal or sodium metal growth.
All right. Very interesting. That kind of folds into some of the other questions we had relating to those plating or those layers. Someone asked about, well, one, someone asked, is there a coating or active material on the aluminum in those on the cathodes in those lithium ion batteries?
Yeah. So aluminum foil is quite standard. So we don't in our lab we don't do special treatment of the aluminum foils. It's very thin, and what we coat on it is just we make a slurry. The slurry means that you mix this powder with some kind of a liquid, and you can then coat this slurry a very dilute slime and coat these particles on the surface of aluminum. You don't have to worry about coating some other extra stuff on the aluminum foil. You can do that. Somebody would believe there is an oxidation layer on the aluminum foil, which is true. But in most cases, you don't have to worry about that thin layer, because here, the aluminum foil is really just providing electrons. Electron can easily go through that oxidation layer. But as I said, some people found that if you can remove the oxidation layer, and it can slightly improve the performance. Yeah.
Okay, great. So the other plating question we had was about the graphite layer. So it looks like, as things are developing, they're trying to remove graphite from the equation, from the ingredient list. They asked, why can't they put a tiny plate of graphite in between those layers? Does it not lend itself to that?
Maybe let me check the question.
Sure. He said, yeah, if I read it. So they asked, why can't they put a tiny graphite plate in between? And I'm not, this is an earlier question, so I can't remember which slide we were on.
In place the graphite particles between. I didn't see the question.
Maybe they can, maybe they'll be able to contextualize that for us a little bit here in a moment. In the meantime, I'm sorry.
Yeah, but I can try to, let me try to understand that question. So adding a layer of graphite.
So they're asking in terms of stopping the whiskers from growing, would a tiny graphite plate work?
Right. You actually don't have to. Depends on what you really want. What is the actual function you're imagining? If you think that we can, well, let me put it this way: you are definitely right, because the pioneer didn't invent the lithium-ion battery in the first place. They invented the lithium-metal battery. And it was because of the whisker problem. They introduced the graphite so that lithium ions will not be reduced into lithium metal, so you don't have to worry about the whisker. That's the advent of this lithium-ion battery. Okay. So that is exactly what you said, using graphite so that graphite can absorb the lithium ions, so you don't have the plating of metal. But now we are reaching the stage that there's no better way to increase the energy density of lithium-ion batteries. And we are going to come back to this old question, outstanding question is, can we stabilize the metal anode so that we can remove the graphite? We can really fabricate a very stable, this kind of a lithium metal battery. Yeah. But in general, you don't have to worry about stop the whiskers. Stop the whiskers that can actually, if you control the current very well, or if you engineer your separator well, which we have a paper explaining this, the separator itself can block the whiskers. Yeah, I hope that is my answer is probably partially can explain that science behind.
Wonderful. It is
Yeah.
a valiant effort for sure.
Uh,
Um, so the next question came up on the ion insertion cathode side, which where we happen to be. The question was, why are the particles distributing the work unevenly in this process?
wow, that's a really a very good question. And I can tell you that most people believe that, and I think that's natural. I had the same doubt. It's because by looking at the structure, it's not uniform, right? You have a particle size distribution. You have different particle size, right? You have the different particle shape, and maybe the particle some particle have the good contact, electrical contact, so electrons can come in, so ions can come in even more easily. Some particles don't have this good contact. Some particles have the easy access to the liquid electrolyte. Some particle is not fully wetted by the electrolyte. But for this one, what we are focusing on is not a structural reason, okay? It is because something more fundamental related to something called thermodynamics of the particle. And if I can expand this topic a little bit, is that when you see this color coming up, and we call this, you can see here for this initial blue color, and we start to have some orangish red color, we call it red, let's assume it's red. The emergence of this red color can be more accurately characterized by a scientific term that's called nucleation. It's like you start to have ice flakes in a cup of cold water, right? You have this nucleation. And even for the identical particles, because of this emergence of new color involves this kind of a physical process called nucleation, you have this nucleation barrier. And that means these particles, even if they're identical, they still need to compete for the chance to nucleate. Once one particle got nucleated, have this new color start to sweep across the particle, the other particles have to wait. Okay, this is really need a lot of explanation, but basically what I would suggest that if you're really interested in this, you have to understand the thermodynamics of the material, which later, if you come to WashU, I can teach the material science course for you. But generally, the majority in this field would believe the structural reason, non-uniform distribution of the particles, particle size, particle shape, the contact with different materials in the environment could be the reason for their random reaction. Yeah.
All right, really fascinating. It leads right into the next question about those color changing, those moving colors. Someone asked, would you still see blue particles when the gold particles are in the majority, or would the other particles already be like phased to that red stage?
Yeah, that's a very good question. Yes, you will see it because in our experiment, our electrodes are not optimized, and you will always see some particles that doesn't have good contact that will hang in there, like just that are not so active. But ideally, if you really have to optimize the electrodes, all particles eventually should reach the same state. If one particle doesn't, that becomes a problem. And that is why we need this kind of visualizer technology to identify why this particle did not participate in the reaction. But if the electrode is in good shape, is in good condition, all particles should reach gold color.
Wonderful, thank you. They're asking really great questions. And by the way, the question that came in about the graphite plate, they said that was really helpful and made a lot of sense to them. So you did a great job of getting at the heart of what they were asking.
Yeah.
So we had also some questions about some folks were looking at the periodic table, and they noticed that, let's see, we had two questions that kind of came in at this roughly the same time. So they noticed that lithium and sodium are in the alkali metal
Yes.
column. And so the questions that have come in are about other metals, other alkalis.
Yeah.
Would potassium work, and how would it affect the performance, for example?
Yeah, that's a very good question. So basically, we are working on all their alkaline. Well, not all, but at least the lithium, sodium, potassium. Potassium is definitely one of the choices, and we also see that potassium is more like sodium. You can achieve this kind of a potassium ingot, and we will have a paper coming up very soon. And you can. Oh, by the way, you guys can access my paper on my website. So you can achieve this ideal deposition. But for potassium, you have to find the right cathode to enable really this very good cycling performance for the anode-free system. And that's still a challenge. And eventually it will go into the question about what is the right electrolyte. And the battery, believe it or not, eventually what determines the performance is the electrolyte. And electrolyte play a very, very critical role here. Yeah. But other than this alkaline metal family, the alkaline earth metals are also possible. So magnesium, calcium, and also the other side, aluminum can also be a choice. Yeah. Or even zinc, yeah, could also be used as a metal anode.
So interesting. So many possibilities.
Yeah, so many possibilities. Yeah.
So currently, I think we had maybe just two questions left. So if anyone has anything they want to ask, this is a good time to put that in the chat. So someone asked, what are the particles in the cathode? What are they made of, and why do they form particles instead of a single sheet?
That's a very good question. So in our laptop cell phone batteries, the material is called lithium cobalt dioxide. Let me see. I can show you the chemical formula over here. So it's the lithium cobalt dioxide. This is the material won the Nobel Prize in 2019. It was tested by Professor Goodenough in University of Texas at Austin. And and there are also other options. And on the final page, and I listed here, it could be lithium iron phosphate. So you can see how it's a lithium lithiated phase but you have iron, you have phosphorus, you have oxygen. So they are really dirt-shaped materials. And you can also have some, this is the acronym or abbreviation, means nickel, cobalt, aluminum, or nickel, manganese, cobalt at different ratios in that chemical formula. There are many different choices. The reason that we don't make it into a sheet is because this material are in general called ceramic material. It's like when you have the table salt, right? You have a bottle of table salt, they are granular materials, they're particles. And the reason that they're rigid. And it's very, very challenging to make it into a single sheet, large sheet, as large as our size of our battery. And also it's not necessary to do that for two reasons. First is that even if you can make the sheet, you eventually want to cut it into different shapes, right? And you will generate some cracks, you will generate defects. That's not what you want. But more fundamentally, you want these small particles so that when lithium ions want to go into these particles, they can go into it very quickly. Imagine you have a very large kind of a shape. Lithium ions enter this particle. It takes a long time to reach the center, right? So you always want to minimize the size of the part of this intercalate or host material. And when you want to minimize that, you don't want to just minimize one dimension because the particles can go from different facets. So you want to minimize all dimensions, the 3 dimensions, and that leads to the choice of particles. And practically making particles is a lot easier than making sheets.
That would definitely play into it. um, so one of the questions we had kind of early on, I wanted to save near the end, was a question about recyclable batteries. I know that's a concern a lot of people have, is that we have these batteries, they get used up. What do we do with them? Would these anode-free sodium batteries be recyclable?
Yeah, so recycling of batteries are really a very urgent issue now. And there are definitely technologies to recycle batteries. And so basically, if you talked about, if the question is only about the anode-free system, I would say it's just easier than the traditional lithium-ion batteries or sodium-ion batteries because we don't have to worry about separate the anode material out. So it's even easier. But the challenge here is that even for the current technology for recycling spent lithium-ion batteries is not ideally efficient. And it still create some not so environmental friendly waste. That is definitely one direction we are looking into, but it's really challenging because you want to harvest all the valuable materials, but remember that when you create that material, you want to create a very stable one, right? So that the battery can last longer. So it's not so easy to crack them out when the batteries reach their end of life. The current solution, more practically or pragmatically, is that the battery, use the battery from the electric cars will be screened for other purpose. You screened and then used for other purposes. Yeah. Really? Basically delay the start of the recycling.
Yeah, the reuse part of that cycle instead of the going straight to recycle. Yeah. Someone asked that dovetails into this other question about why do batteries wear out over time? Why do we?
Can you say that again?
Why do batteries wear out over time?
Yeah. That's a very good question. And for this rechargeable batteries, why do they wear out? Is because think about a bookshelf, right? We have enough space for the book, right? But what if the bookshelf it does not fit the size of a book? And imagine you have a very rigid book. So you have to cause some deformation of the panel, right? The shape of the bookshelf has to be changed. And we are having this. When lithium ions go into the particles, you will generate the local distortion of the crystal structure. And when you do this once, that's okay. It can accommodate it. But when you do this thousands of times, it's like you're bending metal wire. It got fatigue. It will break. And the battery particles can break due to this repeated ion insertion and extraction, and you have the volume contraction expansion, and that causes the loss of contact with other particles. And this is one point. And the other key point is that you will lose your electrolyte because of side reactions. And when you don't have electrolytes, when the swimming pool doesn't have water, you won't be able to swim, and the lithium ions won't be able to swim around the particles. So the reaction basically will just stop.
Sorry, technical difficulty there. But our last question that we currently have is, will the anode-free sodium battery technology be safer than the lithium ion and the lithium and other lithium batteries? Is it the electrolyte that is used as flammable?
Yeah, whether it is safer depends on how you use it, and because when we say the safety issue is really just the little metal structure going through the separator, and that depends on the current you apply to the system and depends on the temperature. So there is no absolute better or not. It really depends on the environment that you're using or the condition you're using. And the electrolytes, because that's non-aqueous electrolyte, it's basically oily. It's like oil, so it's highly flammable. Otherwise, we don't have better choices, because otherwise, if you have some aqueous electrolyte, it will react with the metal, with the alkali metal.
Wonderful. So I think that's the last question we have, which is bringing us right up to our time. Oh, well, there's one that just came in. How is a macron to scale is the question.
So micron, so MICRON is just another name for micrometer. So it's a 1/1000th of 1 millimeter. Yeah.
Perfect. Short and sweet for the last question.
Yeah.
So the questions were fantastic, and so were the answers. And I think I'll turn it over to Rose if she has any final thoughts or comments before we sign off.
Well, thank you very much, Dr. Bai, for sharing with the St. Louis community tonight. Your work and your research, it's fascinating, and we had a lot of good questions, I think. And it's important work. And the only thing that I would have to say to those of us who are still here is that I did post a link to Dr. Bai's faculty webpage in the chat, so you can scroll up if you would like to know a little bit more about his work and research. You can click on that link. And then I would ask that you take just a moment to let us know what you thought about tonight's event and any ideas or thoughts about future events. And I'm going to go ahead and, by filling out our online survey, and I'm going to go ahead and post the link to that in the chat window now. So that'll be up for a minute or so. If you click on that link, it'll open up another window in your browser. And if you take a minute to fill that out, that really helps us a lot. So I'm going to pop that in there now. Okay. And then I'm going to go ahead and post both a link to the Academy's YouTube channel. If you're interested in even more science and STEM, you can visit our YouTube channel. We post a lot of our public seminars and talks there as well. So I think that's all I have for the evening.
Wonderful. Thank you. Thank you again. We really appreciate this partnership and being able to share such fantastic research that's going on right in our backyard, so to speak. So thank you all.
Exactly. Yeah, thank you for having me. It's great to talk to our St. Louis next generation guys, engineers, scientists. It's very exciting. Yeah, I like the questions, and they really are right to the point, asking the key question, not only the right question, but the key questions. That's really impressive.
Yeah, it is, isn't it? Yeah. Well, thank you for joining us all this evening, everyone. We really appreciate it. And again, there's a link to Dr. Bai's faculty webpage in the chat. And again, if you take just a moment to fill out our survey, we appreciate your feedback.
Thank you all. Have a great evening.
Thank you. Have a great night. Bye-bye.